Hello everyone, we are from Group 10 and today we will present our DSP filtering graphical analysis map. Our process begins by loading an audio file into the MATLAB using an audio read function. We then remove a DC offset by subtracting the mean value, ensuring the signal is centered around 0 for accurate analysis. Next, with this pre-processed audio, we perform sampling. Since digital signal processing operates on discrete time signals, the audio must be represented as a sequence of samples. The sampling plot shows the first 500 samples of an audio signal using a stem plot, which clearly displays each individual sample and highlight the discrete nature of a digital signal. However, the time domain signal does not reveal the frequencies present in the audio. Therefore, we apply the DTFT to transform the signal into a frequency domain. The resulting spectrum shows the dominant frequency components and helps us identify unwanted noise frequencies. Based on this frequency analysis, we can determine an appropriate cutoff frequency and design suitable FIR and IIR filters for noise removal.
Based on the frequency information obtained from the DTFT analysis, a cutoff frequency of 1800 Hz was selected. An FIR low-pass filter was designed using the Hamming window meters with filter order 40. So why the order is 40? Because it provides a good trade-off between performance and complexity. It gives a sufficiently sharp cutoff at 1800 Hz to remove the high-frequency noise effectively. Then, why we choose the Hamming window? Because it gives a good balance between the noise reduction and preserving the original audio. Therefore, the Hamming window with order 40 achieves a good balance, with effective noise reduction, sharp transition, and preservation of the original audio. Next is the FIR impulse response. The impulse response represents the FIR coefficient. As we can see, the FIR response brought by the MATLAB is symmetry above the center, indicate a linear FIR filter. This means all frequency components experience the same delay, preserving the original waveform shape. Next is the FIR magnitude spectrum. The magnitude spectrum verifies the filter performance to verify whether the filter removes the correct frequency. As you can see, the magnitude spectrum brought by MATLAB, frequency below the 1800 Hz cutoff are preserved, while the frequency above the cutoff are attenuated. This confirms that the filter effectively removes the unwanted high-frequency response. Next is the FIR phase spectrum. The phase spectrum is used to analyze phase delay and check whether the system causes phase distortion. In our phase spectrum, the phase is nearly linear in the passband, which confirms the FIR filter has linear phase characteristics and preserves the waveform shape.
Building directly on the DTFT analysis my teammate just discussed, we extracted our cutoff frequency and determined our filter order. For this IIR filter design, we chose a second-order low-pass Butterworth filter. An order of 2 provides an ideal balance, a smooth roll-off to reduce high-frequency noise while remaining mathematically simple and stable. To translate this into a digital domain, the bilinear transform generated our system coefficient shown in the stem plot. For our second-order filter, we can clearly see 3 required values at indices 1, 2, and 3. The B numerator coefficient in blue, which detects the feed-forward path, and the A denominator coefficient in orange, which control the feedback. With this coefficient defining our system, we first examine the impulse response to verify the behavior of the time domain. Looking at the graph, you can see the initial spike followed by the ripple that continue indefinitely. This visually confirms the recursive feedback loop driven by our A coefficient, which is a defining characteristic of an IIR filter. Next, we use the magnitude spectrum to verify the filter provide the required low-pass characteristic. The plot displays a smooth passband and gradual downward roll-off. This confirms our Butterworth design successfully preserved useful audio while frequency above cutoff are smoothly attenuated downward. We also do for the phase spectrum to check for the phase delay and potential phase distortion. The graph shows a distinct non-linear downward curve. This indicates a frequency-dependent phase shift, meaning different frequency experience slightly different time delay, which can cause slight signal distortion. This is standard trade-off we accept for the smooth magnitude response of an IIR filter.
After designing the FIR and IIR filters, we use a Z-plane to understand how the filters behave. For the FIR filter, we use this code, and the denominator is 1 because FIR filters have no feedback. Since FIR filters are stable by design, the Z-plane is mainly used to observe the zero placement. The zero shows which frequency components are reduced. For the IIR filter, we use this code, and the IIR filter uses feedback, so we need to check the stability. In our plot here, the poles are inside the unit circle, which means IIR filter is stable. Next part is the convolution for the FIR filter. All previous stages only analyze or design the filter, but convolution is where the filter is actually applied to the signal. The formula is Yn equal to Xn multiplied by Hn, where the Xn is a noisy audio and Hn is the FIR impulse response. As Dr. Musa always mentioned, 0 can represent remove and 1 can represent preserve. In our FIR filter, the coefficient works like weight that reduce the noise while preserving the main audio signal. We do not show the convolution for IIR because IIR has an infinite impulse response, so direct convolution is not practical.
After applying the FIR and IIR filter, the tat noise is successfully removed. However, the E sound is still present. So let's zoom into the blue box to see what happened on it. The E noise occurs at around 690 Hz and 800 Hz, which are below the low-pass filter cutoff frequency of 1800 Hz. Therefore, this frequency remain after low-pass filtering. To remove them, a notch filter is applied. Next, this figure compare the original audio with FIR and IIR filter output. The original signal contained tat and E noise, making the waveform rough and noisy. After FIR filtering, the waveform becomes smoother and preserving the main audio information. The IIR filter also reduces noise effectively. Overall, both filters improve the audio quality significantly. Now, let me demonstrate the original and filter audio.
0125.
The original audio contains tat and E background noise. After applying all the filter, most of these noise are removed, resulting in a much clearer audio signal. So now let's listen and compare the difference. This is the FIR filter result.
0125.
And this is the IIR filter result.
0125.
Finally, the clean audio is saved as a new wave file. This completes the filtering process and allows us to evaluate the effectiveness of the noise removal. So that's all from our group. Thank you.